This video lecture concludes the electron configurations part. So you'll want to watch electron configurations part 1 before watching this video. So just as a quick review, we're looking at the energy orbiting, the energy ordering of orbitals. So we have electron spin, which dictates that there are only 2 electrons per orbital sublevel, because no 2 electrons can have the same 4 quantum numbers, and that this sublevel energy splitting is a result of Coulomb's law, shielding, and orbital penetration. So again, if these are unfamiliar to you, you'll want to go back again and review the first half of this video. So now that we've figured all of this out, it's finally time to start adding electrons. So we like to use what is called the Aufbau principle. It is a goal of it is to minimize the energy, and this is a German word meaning to build up. And so what this means is that you must consider the ground state when solving configurations. So this is one way to think about it. So you follow it through like a snake. So the arrow points to the direction that you're going to go first, and then you loop back around. Then you fill the 2s sublevel, then the 2p, then the 3s, and then the 3p, 4s, 3d, 4p, 5s, and so on. If that is confusing to you, and it is often confusing to me, I prefer this because you can see the increasing energy and it looks more like a graph that I'm used to. Again, just pick whichever one makes the most sense to you. So here you see that the 1s to 2s, 2p, 3s, 3p, 4s, 3d, 4p. So it follows the same snake pattern as the previous one. It just is vertical instead of at an angle. So then the last thing that we need to talk about is Hund's rule. I think German for dog, I think is what that means. But basically, when you're filling the orbitals, you fill them singly first before pairing up. So as an example, we have our carbon. So how many electrons are there? Well, there are 6 total. Oops. And so our electron configuration would be an S. We have 2 in the S, and the rest would be in the P. But if we wanted to put that into the orbital diagram, it will look like this. So both of these show 2p2, but in this one you have electrons pairing up rather than separating at first. So electrons don't like to do that. They like to line up with parallel spin first, and sorry again, they don't like it, that's just what they do. The magnetic field and their angular momentum causes them to have a lower energy when they line up in separate orbitals with parallel spins. So this is what we actually observe. We do not observe this. And there are ways that this can be tested. So when filling the orbitals, you want to fill them singly first before pairing up. So one way to think about it is the good old bus rule. So when you get on the bus, you want to get to your closest seat. So you enter the bus and you sit here. And now there's 2. So now we have to climb the stairs to get to the next level. And both people sit there. Well, okay, now we get up to the next level. So you're already climbing stairs. So you get here. So then if you're already climbing the stairs, why would you want to sit with somebody? Everybody wants to have their own seat on the bus or the train, so you sit by yourself. So oxygen it behaves the same way. These will pair up first because they're lower energy. It takes less energy to not climb stairs, to climb 1 flight of stairs than it does 2. So we would fill our 1s orbital first, then our 2s orbitals, and then our 2p orbitals. So we've got our 4 here. We have 8 electrons, so now we need to have 4 arrows. So 1, 2, 3, 4. So each one of these fills with parallel spins, and then the last orbital here, 2p orbital, gets the second down electron. So again, remember the up and the down arrow indicate the spin, which is that m sub s quantum number. And if we want to write out our electron configuration, 1s2, 2s2, 2p4. So the exponent is the number of electrons that you have in that level. So let's think about what quantum numbers would go with these electron configurations. So let's think about what are the 4 quantum numbers for the 2p electrons. So before we can answer this question, we have to review our quantum numbers. So our n, which is our principal, this is the overall size and energy, and those are the values of 1, 2, 3, and so on. So they start at 1 and they go up as integers. Then we have our L, which is the angular momentum sublevel, and this is what determines the shape. And so we see S, P, D, F, G, and so on. And so the numbers that we could indicate this would be 0 through n minus 1. So if you've got a 2 for n, then you've got 0 and 1 are your possible values for L. However, it would look really confusing to have a bunch of numbers right next to each other. We wouldn't really know what they meant. And so we use letters. So S, P, D, F, and then after F, they just go in alphabetical order. Then we have our magnetic, which is the orientation of the orbital of the sublevel, and that's negative L to positive L, and then our spin. So what might this look like? So if we want to start off with our 2p, so the easiest one is going to be our n. The number is right there, it's a 2, so our n is equal to 2. Now we have our L, so our possibilities for L would be 0 and 1, okay? So, but we're in the p, right? So there's 2s and 2p, but we're in p, so we know that our L equals p, or you could also say it equals 1. Okay, so now we have this tricky one, this orientation of the orbital, and I actually have a picture to kind of show you what it looks like. So this is the orientation. So don't worry so much about the actual shapes here. This is just, remember, the probability that we'll find an electron in this area. And this goes from -1, 0, and +1. So for our 2p electrons, 2 of them can have a -1, 2 can have a 0, and 2 can have a 1. So those would be our m sub l's. And then our m sub s. Every 2 electrons, they can't have the same 4 quantum numbers, so we would have +1/2 and -1/2.